Hello, everybody. So let's start uh, today's session. Today's session is on clustering. Specifically, we will discuss k-means clustering. So I'll share my screen. Let me know if you can scan screen. Yeah. So you can see the screen, right? Can just type in the chat box if you can see the screen. Right. So yeah. So let's start this thing. So just I will go over the K-means clustering algorithm once before solving some more problems in that. So yeah, so this is just a precursor problem, just that. So these are the data points given, like minus 2 comma 2, 1 comma minus 2, and 2 comma 1, and 1 comma 2. So we have to find the data point x, which has the highest average distance with respect to other data points. Right. So yeah, this is a problem. So this is this functionality is very much required in for k-means. I mean, you don't need the highest average distance. You probably need the minimum distance. Um, yeah. This is very simple, right? So the answer is minus 2 comma 2. So basically, what we will do is very simple. It is you are given this points x1, x2, x3, and x4, and you are asked to find the point which point has the maximum average distance with respect to others. So that means first you consider x1, right? Distance to itself is 0. You don't want to include that itself. Again, distance to x2, right? You have to evaluate this distance. Euclidean distance, typically what we consider is this thing, right? The 2 norm square, and like this, x1 minus x3 and x1 minus x4, right? You are given the 4 points, x1, x2, x3. So let's call this as the x1 square, right? D square of x1, right? Similarly, you evaluate d square of x2. Now x2 is with respect to x2, you have to compute everything, right? So first term will be x2 minus x1 whole square plus 0, because x2 to x2 distance is 0, right? So again x2 minus x3 and x2 minus x4, right? Yeah, basically just find um, the maximum distance is enough to find the square distance. What ideally what you are supposed to find is the average distance, right? So that means ideally, I mean, if this were asked in theory, just what is the average distance of point x1 to the other points, right? Just may allow somebody else, right? So yeah, I mean, let's complete this. So This is how you do d square of x3 and d square of x. All right, so yeah, I think that's it. So if you do that, what you get is this thing. So max distance is the first option. Sorry for the typo, B, C, D, E. This is A, B, C, D. I mean, the 51 represents the distance d square, whatever I have written, from minus 2 comma 2 to every other point. Right. So the answer is 51. Okay. So let's come to what is Clemens clustering. Clustering, because the rest of the six questions are completely based on this Clemens clustering. Right. So I'm sure you would have gone through, but just for the sake of it, let me revise it. Right. So Clemens clustering, what is the optimization problem you solve is this thing, right? Let me explain what is that. Okay, so your objective function is this thing, right? This is this, right? And you have n is equal to 1 to n, and your k is equal to 1 to k, and you have r and k. Again, you have xn minus mu k, right? People write mu as the centroids, mu k. So this is the optimization function that you end up minimizing in the k-means clustering algorithm. Right now, R and K, J is a function of what is given to you. You were given with xn's, right? So typically you have given with some data points, some clusters, right? You don't know a priori which clusters they are, right? And it's an unsupervised algorithm. So this is what you are given with. Now your task is to find this cluster center, and you don't know how many clusters are there a priori, right? So this J is a function of R and K and mu K, right? So what is R and K? R and K is takes values 0 or 1, 0 or 1, right? One is all right. So R and K takes value 0 or 1. So it takes a value 1 if the if your nth example is assigned to cluster K, right? So let's say here you have let's draw it properly. You have 16 points, right? Now this can be x3. Sorry, let me write it. This can be point 0.3. This can be point 0.8. This can be point 0.11. This can be point 12. So this is say 1. This is 2. This is 3, and this is 4. Right. So what we have here, let's say put it this as number as 1. You have 1, 8, and say 11 and 12. Right. So that means x11 is 1 and x8, sorry, r81 is 1. That means in this example, just focus on this. This means our eighth data point is assigned to cluster 1, right? That is 1. In this case, it is assigned to cluster 1. That's why it is 1. Otherwise, it is 0, right? So this, your optimization in K-means is this function J, and this function is, I mean, you optimize over variables, right? What variables you optimize? These are nothing but R and K and mu K. Mu K are nothing but your cluster centroids, and R and Ks are the hard assignments to this cluster centroid. So we have a softer version of K-means, which is called as Gaussian mixture models, that we will discuss in detail in the next week, right? So yeah, this is what is basically the optimization problem in K-means. right? So what do you do? So because J is a function of your RNK, and this is a difficult optimization. This is not a convex optimization to solve, right? This is a function of two variables. So what you do is you fix certain mu k's, right? So first step is fix mu k and optimize RNK. Optimize your RNKs, right? Since J is a function of RNK and mu k. In the second step, right? Second step, you fix RNK as you have got from your step one, right? And optimize your mu case. Right? This is an alternate optimization. You do step one, then go for step two, again come back to step one, again go to step two, right? Till convergence, you have to repeat this, right? So let's say we have fixed, say in this example, we have fixed certain cluster centroids. You don't know initially where the ideally you want four cluster centers, which are the centroids of this thing, which I have drawn, but ideally you don't know. So you may initially assume you can initialize cluster centroid somewhere here, right? So what do you do is for all the data points, for every cluster, say every xn, every data point, you find the distance to the initialized means. Say you have mu1, mu2, mu3, and mu4, right? For every data point xn, find the distance to, say you have initialized mu1, mu2, mu3, mu4. Find whichever clusters this point is closer, right? And then assign Rn, comma, whatever k, right? Which cluster, kth cluster, if it is closer, assign it to 1, right? So that's all. This is your first step. And do this for all the data points in your training set. In step two, because each mu k depends, it doesn't depend on mu1, doesn't depend on mu2, right? So it just, you have to simply optimize mu k. It is nothing but a quadratic, right? So if you differentiate for mu k's, right, this is what you get, right? So why it is means, why do we call it as k means, is it is very simple. RNK takes values of 1 and 0, right? So it is basically for cluster K, you are just computing the average of all the points that are assigned to the cluster K. That's why the you can say, you can think that the name mean is coming, right? So K means algorithm. That's it regarding K means, and I hope it is clear. If you have any questions, you can ask me. Right? It's a Ridge formula. Oh, I did not get. Can you elaborate what do you mean by Ridge? Anyone? I think someone has written the Ridge formula. I don't know what do you mean. Okay. Uh, we will move on to the problems if there are no questions, right? So Yeah, so which of the following is not true about K-means? Any answers? Oh, ridge regression formula. Ridge regression is, I mean, it's a totally different setup. So basically, it's a regression by definition. It is supervised. Um, so and ridge regression is nothing but you are performing your regression task with the L2 regularizer. So yeah, it is very much different from ridge regression. If you have anything any questions there, we can further discuss. But yeah, it is very much different from ridge regression. This is an unsupervised framework. So B, yeah, so that is correct. And because you don't overlap the clusters in k-means, right? And others are all correct. It is an unsupervised learning because you don't have any labels, and it is hard clustering technique. Anyone knows why it is a hard clustering technique? You guys, I mean, this question can come, right? Why? What is the reason to call k-means a hard clustering technique? Anyone? So the reason is this thing: your R in case, right? The cluster assignments, right? Ideally, these are probabilities. If you next week we will discuss more details about this thing. But R in case are zeros or ones, right? Yeah, these are hard values. Um, so it need not be zero and one. You can assign any real number between zero and one, ideally, right? So that means nth this nth data point belongs to now it is like it belongs to mu1 and it doesn't belongs to any of the other clusters, right? So in probabilistic cases, right, this Gaussian mixture models, it's like n point n belongs to mu1 with say zero point 0.1 probability, right? X and n point belongs to cluster mu3 with say zero point 0.3 probability, like that. So that's a soft assignment of points to clusters. Now here that the only reason is because R and Ks are zeros and ones, right? So that's the reason it is hard cluster. Um, okay, so I have a question later on, like on K. How do you choose K for K means? But yeah, for now, K is a hyperparameter of the algorithm. Okay, so yeah, right. So the few questions are based on programming. So the code link is given, so you guys can go ahead and uh, run that, right? So basically, the problem is this: you have an MNIST digit data set. So I'll describe what this data set it is and what is the problem and what you are supposed to answer. So just go to this link. The solution is given. Go to this link and just run the code, right? So I'll explain what is asked basically, right?
Hello.
Yes.
Yeah. Yashwant, if you don't mind, could you please show all the questions in the assignment that we will be solving today? Just could you scroll with the
Uh,
assignment set?
yes, that's it.
Uh, I suppose then from this, the remaining questions, are they all on the program that we are going to discuss?
Not really. Not really. I'll be explaining some details on what is this R, and there are only two programming questions.
Okay.
and I'll explain how the K is chosen. Right.
Yeah, we would love to discuss this programming questions, but just for my information, do we have these kind of questions? I mean, programming
No,
based questions
no, you will not get.
with the
You will you will definitely not get programming
we won't
questions.
get these, right?
No, 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 not at all.
Okay, okay, no issue. Thank you so much.
Yeah. So, okay, so let's go to this thing, right? So yeah, MNIST is a digit data set, right? It's a digit data set. Basically, if you see this data set, you have zeros, one, two, three, four, five, six, seven, eight, and nine. Okay, so that's why you are asked to initialize with 10 clusters because you have only 10 digits of classes in that data set. And you have, I suppose you have the thing 60K training examples. Roughly it is divided by 10, 6,000 examples for each digit, roughly. And I think you have test of 10K, testing of 10K, right? This is train and this is test. Yeah, so you are asked to run a k-means algorithm on for this data set. Now each image is 28 by 28. Okay, this is not 2 by 2, right? So just for visualization purposes, right, we can have say this is some say cluster one, cluster zero, and cluster two, and so on, and cluster four, and so on, cluster five. So hopefully I mean, you cannot visualize this in 2D, definitely for sure, because your dimension of the data is 28 cross 28. They're huge. So um, yeah, so what you can do in this, if you want to visualize this thing on 2D is you can use your PCA, right? And reduce this dimension from 28 by 28 to 2. Okay, then try doing the k-means clustering. So probably you should get something like this, right? So let's see what was the question asked. Right, you're asked to do this, run the k-means clustering algorithm on this MNIST dataset and predict the labels. So how do you predict the label? So basically what you have to do is label the prediction class for all the points in a cluster as a majority true label, right? So yeah, this point, right? Yeah. Now any training test example that comes, right? Say it is coming from an example one, right? Now what you do is because you have 10 clusters, right? Take the nearest cluster. Um, so when I say you have all the cluster one has need not contain all the true examples. There is some inherent noise in this, right? There can be some examples. Say if one instead of one something nine is written, something like this, right? Probably it can be treated as one, so that example can come here. Similarly, for nine, one can be written something like that, right? So there is some noise here, right? So when a test example comes, find the closest centroid to that. Hopefully, it is one, and there you find what is my majority of the uh, labels are, right? So in this, if my majority of the labels are saying one, right, I assign the prediction one to this example, right? So that is what you are asked to do in this particular programming exercise, right? So what do you get? Accuracy is 79% if you do this thing. right? So yeah, yeah. So another point, another programming a follow-up question was to evaluate this RAND index, right? Now, what is a RAND index? Let me discuss this thing and let's go on to solve this problem, right? What is RAND index? Let's say you have it is to measure how to compare two different clusterings. Say there is a set S, training set S, right? Where you have some examples x1, x2, and so on, xn, right? And now you have two sets of clusters. Say now you have S1, S2, and so on, Sk, right? Again, here you have say Y as S1 prime and S2 prime. These are clusters, okay? And that means each S1 is a set of points which you have clustered using some, let's say, algorithm. Say this is M. K need not be equal to M. Now you want to measure how similar or dissimilar these two clusterings X and Y are, right? So here what you do is you choose a pair of points, right? So how many possible pairs you can get from your training set is and choose two, right? Now what you do is for every pair you check uh, if they belong to same cluster in this X and Y, right? So that is nothing but A. A is nothing but set of all the points which belong to a same cluster in X and Y. And B is quite opposite, is set of all the points which belongs to different clusters in X, right? Cluster, same cluster. And here it's a different cluster, right? A different cluster. And basically what you end up doing is you just add them. How many, basically it's like how many pairs on how many pair of points your clustering algorithms X and Y are agreeing. Either they are same or different, but they are in agreement over all the possible pairs. That's it. It is some kind of, you can say, vague version of accuracy, right? But it's not accuracy. Right? So this is what is RAND index. It captures how similar two clusterings are, two different clusterings are, right? Okay, so yeah, that's it. So now you have given two clusters. So one is like you have ground truths in the earlier example. Another one is the clustering that you have came up with running k-means, right? So what is the RAND index? So you have the code. You can just run that. So answer is 93 as your RAND index, right? So now is an interesting question. This is not a programming question. A is RAND index, as I have explained, right? Um, right. So this is a pair of points which belong to the same cluster, and B is nothing but a pair of points belonging to different clusters. So then, how is the RAND index and accuracy are you know are the same? RAND index and accuracy. So accuracy is this thing, right? Um, and RAND index is this thing. So are they same or not is the question. So yeah, you want me to explain in Hindi because I'm okay if everybody is can understand Hindi, right? So uh, yeah, guys, uh, right. So basically, these two are different concepts. So by very definition, what RAND index is doing is it is evaluating the agreements for a pair of points, not for an individual point. Accuracy, you see, for every point you call, is it true predicted or false predicted, right? So intrinsically, it's very much different concepts, right? So they are nowhere related. Frankly, you can say, I mean, intuitively, you can think of it as an accuracy in clustering sense, but when you correlate, I mean, you try to compare it with the real accuracy, right? It is very much different, right? So, yeah, any questions? Okay, let's stick with English itself. So, yeah, okay, this is an interesting question, right? This question you will end up uh, in many places. I mean, if you go for any interviews, right? People typically ask, how do you choose the K, the value K in clustering algorithms? Right now, right, so when you start with you when you want to cluster, right? Right, what you have is that set of data points. That's it, and you don't have any other information. Right now, it is by looking at this, whatever I have drawn, you can easily say there are three clusters, right? But this is a two-dimensional data. As you have seen, you have a data dimensions that is of 28 cross 28. It is highly improbable to, you know, uh, see what how this looks like. Anything beyond three dimensions is painful, right? So you have to resort to some techniques such as PCA, T-SNE, right, to visualize into two dimensions. But the data itself, you cannot visualize as easily anything beyond three dimensions, right? So the natural question that arises is, how do you choose this value of k? K is equal to 3 is apt for the figure that I have drawn, but you don't know how beforehand that k is equal to 3 works. So basically, how do you choose this k? Right. So what happens is, in practice, as I explained, there is this distortion measure for clustering is this thing, sigma over n, sigma over k, and this is r and k times norm x minus mu k square. Right. So you start with this thing. K, you start with very small value. Okay, so definitely your measure of this distortion will be higher, right? And after a certain point, right, your value of k will be very, you will not get that much improvement even if you increase k. Of course, the worst thing what you can do is k is equal to set k is equal to n. Every point is the centroid of itself. That means you get a zero error there. You don't want to do that. There's no information you're doing. So this is k and this is d. Like typically for this kind of techniques, you have this kind of an elbow, right? Like people call it as an elbow, right? So where you see the sharp, where you stop seeing incremental gains, right? You can set up some threshold, like if I increase k, if my gains are not more than some delta, right? I stop my uh, algorithm, right? So this is your optimal choice of k in practice, right? This is elbow method. This is elbow method for clustering. Okay, so yeah, that's what it is. And yeah, what happens as you as if you increase the value of k, right? If the value of k is too small, um, right, your error is too high, and you can think of it as you are underfitting too much, right? I mean, you are not learning anything basically. So basically, what one of the example is when k is one, all you can get is this thing, right? So this is meaningless. I mean, you don't get any information from this. And another instance is k is, let us say, let me put k to be uh, how many points we have? 8 points, right? So let's say k is 8, right? You can have this as a cluster, this as a cluster, this as a cluster, right? Even this is not a good clustering because there is not much space between these data points, right? Ideally, you want all this to be in one cluster, right? Probably if that kind of k, even though this kind of k, right, gives you very low error, that is this regime, right? But it's not desired because you are not learning much. The worst form of clustering, you can say the data itself, right? The number of points itself, right? This is a cluster to itself, right? So you have 1 point, you have 1 point, you have 1 point, something like that, right? All the data points are your cluster. That's the worst point. You have zero error in this case. You don't want zero error, right? So you're not learning anything basically. So when you have too much of k, right, you overfit this data points. And when you have very low value of k, you are underfitting your data. So what is the optimal choice? Is there are other methods also, but this is what people typically prefer. So this is how you choose k. Right. So the answer is yes, you are overfitting the data. Right. So yeah, that's all we have for today. And for next week, I think it will be probabilistic, so it will be more interesting and challenging. Um, right. So any questions? Uh, yeah. So I would like to clarify why the ridge regression is coming here. Right. Basically, it's a totally different concept. Right. What is ridge regression is? Ridge regression. is this thing will come in regression problems basically, right? And it is totally a unrelated concept uh, compared to this thing, uh, your clustering, right? So what is rigid regression is, let's say you have any model X, and that is going through some parameterized model, and this model can be any linear model, a neural network, or anything that can be parameterized parametric model, right? And you're predicting y, right? So ridge regression is a concept that is, let's say there is some error measure between your predictions. So y hat is your prediction, right? And y, right? And typically what you use is your cross entropy loss. And what happens is your typically tend to overfit your data on your training set. To avoid that, what you use is you penalize your weights. So what does this mean is W can be any number of layers if it is a neural net. Flatten out everything and just take the Euclidean norm square. That's it. So this is your ridge regression. So what happens is that it helps preventing overfitting. So you generalize better on your test data. So yeah, compared to this and what we have discussed today, they are totally very much different concepts, right? And this is a hyperparameter that is supposed to be tuned on your validation data. Okay, so I hope this is clear. Okay, guys, so let me know if there are any more questions, otherwise we can end today's session. So next week it will be probabilistic. The same concept, but it will be probabilistic. So what we will discuss is Gaussian mixture models. Okay, guys.